Errors and data analysis. There are three main types of errors associated with any measurement that you take in the lab. The first one of which is the personal error, which we tend to think about like this. Okay, so personal errors should never happen. If they happen, and they might happen, you have to repeat your measurement and avoid them, right? Because if you know that you have a personal error in taking a specific measurement, you have to keep repeating until you get rid of that error. The other type is random error. The random error is there no matter what. We cannot avoid it because it has to do with the equipment that we have in the lab. Don't get scared, we don't have something like this in our Physics 1 labs. Or they are caused by the environment itself. For example, temperature change and stuff like this. Wind, air resistance. So random error cannot be avoided. However, to reduce its effect, we repeat our measurement more than one time. Okay, so you will see that we repeat the measurement 4 or 5 times in order to reduce the effect of the random error. The last type of error that we want to talk about is the systematic error, which results from something like assuming that this is a completely fine ruler and use it to take your measurements. This ruler will always measure longer than the actual length. Now let's talk about significant figures. And what is the importance of significant figures, you may ask? Now let's say that this cat is trying to measure its mass. And let's say that the scale looks like this. So this reading is 20.1 kilograms. This is a big fatty cat, isn't it? Now what if the scale is reading here? How would you write this? Would you write it as 20 kilograms? M equals 20 kilograms and that's it? Now the answer is no. We have to write this as 20.0 kilograms. And the reason is that we want to tell whoever is reading our result that this balance or scale is capable of reading 3 significant figures in our case. Okay, so we have to indicate explicitly that it can read, for example, 20.1, but the reading is 20.0. It is exactly on 20 kilograms. Okay. Now you probably noticed that I said that this number has 3 significant figures. So how did I know? Now there are some rules that we need to take a look at. The most significant figure is defined as the leftmost non-zero digit in your number. The least significant figure is the one that is, you have 2 cases. If there is no decimal point, it's the rightmost non-zero digit. If there is a decimal point, then it's the rightmost digit, whether it's 0 or not. Now, let's take a couple of examples here. Now let's look at the first number. How many significant figures in this number? Now, according to the rule, the most significant figure is the leftmost non-zero digit, and the 5 in this case is the leftmost non-zero digit. So this is the most significant figure in my number. Now, there is no decimal point, so the rightmost non-zero digit is the least significant, which is in this case the 9. So if you count how many significant figures from the least to the most, you will find that there are 4 significant figures. Now let's look at the other example. Again, the leftmost non-zero digit is 1 in this case, so this is the most significant figure. The there is a decimal point, right? So the rightmost digit, which is this 0 in our case, is the least significant. So this number has 5 significant figures. Now there are some rules if you want to add numbers with specific number of significant figures, or you want to multiply them. How would I represent my result? Okay, so this is what all these rules about. Now, if in case of adding and subtracting, I'm going to explain it by using these two examples. Okay, if you want the text or how to do it, it is explained in details in our lab manual. Now, if I use the calculator to add up these two numbers, this is what I should get from the calculator. Now, let's look at the number on the left side. Now, if you look at the rightmost column in my addition here, you'll find that the second number, which is 56.1, doesn't have any significant figures in that column, right? There is only the 6 in the first number. For this reason, we have to drop this whole column, okay? So the 6 in the result should be dropped. And since the 6 is greater than 5, greater than anything that is greater than or equal to 5, then we have to round the number and increase the digit before it. Now the 6 is greater than 5, so the number becomes 79.4. Now, if you look at the second case, you'll find that the answer should be fine, because now the second number, which is 56.10, does have a significant figure in that column, so we can keep the whole answer. Now, what if we are multiplying or dividing the two numbers? Now, here it is very simple. The number of significant figures in the final answer should equal to the number of significant figures that is least in our numbers. Okay, so in this example, of course, this result is obtained directly from the calculator. However, if you look at the first example, you will notice that the 3.26 is a number with 3 significant figures. 60.1 is a number with 3 significant figures, so the final answer should have 3 significant figures. So we should cancel out the 926, which is after the decimal point. And since we're canceling out the 9, which is greater than or equal to 5, then our number becomes 196. Okay, and this is how you should report your final answer. Now let's take a look at the second example, 0.136 times 70 point, and there is nothing after the point. Now, looking at this number, the first one has 3 significant figures because the leftmost non-zero digit is 1. And because there is a decimal point, the rightmost digit is 6. So we have 3 significant figures. The second number, which is 70 point, now the leftmost digit is 7. So this is the most significant figure. There is a decimal point, so the rightmost digit is the least significant, which is 0 in this case. So we have a number of 2 significant figures. So our final answer should have 2 significant figures. Now the calculator gave me this answer, which is 9.52, which is a number of 3 significant figures. So we have to cancel out the 2 in order to convert this to a 2 significant figures number. So our final answer should be 9.5. Error analysis. You have random error with any experiment, and this random error cannot be avoided. And the reason is that it's coming from the environment of the experiment. So we said that we'll have to repeat the experiment several times in order to reduce the effect of this random error. In this example, the time t was measured 4 times. Now the question is, which one of these is the best time that I have to use? For example, if I'm using this time to calculate another quantity. The answer is none of them. To get the best number to use for another calculation, or to report the result of my experiment, we calculate something called the average. Everyone knows how to calculate the average of several numbers. It's the sum of these numbers divided by their number. In this case, the average time is the sum of these 4 times divided by 4. And if you do the calculation, you'll find that it is 0.50 seconds. So I can say with confidence that the result of my experiment is that t equals 0.50 seconds. Now, as you can see, my readings have some uncertainty because not all of them are 0.50. For example, we have 0.51, 0.47, and so on. And these numbers are far away from the 0.50, which is the average time. So to represent the uncertainty in my readings, we calculate what's called delta t, or the average deviation of my numbers. In order to calculate the average deviation, let's define something called the deviation from the mean, or t minus t average. Now the deviation from the mean, and we calculate the absolute value of this number, is how far each of the readings is from my average value. So for example, the first one is 0.51. If you subtract it from the average, 0.50, you'll get 0.01, okay? So the deviation from the mean of this number is 0.01. Now for the second number, it is, as you can see, it is 0.03 away from the mean, and it is less than the mean. However, we're taking always the absolute value, so it's 0.03. The third reading is 0.02 away from the average, and the last one is exactly equal to the average, so there is 0 deviation there. And then finally, once we find these numbers, we calculate their average, and this is what the average deviation means. Okay. All of my numbers have one significant figure, so the final answer should have one significant figure as well. So my answer should be reported as 0.02 seconds. Now, once I get these two numbers, the average time and the average deviation, which is delta t, then I can write down my result as t average plus or minus delta t. In other words, t average is 0.50 plus or minus 0.02, and the whole thing has a unit of second. This is how you can report your answer to indicate the average and the uncertainty in that average. Propagation of errors. Now we know that if you have two numbers, for example, let's say that you have two quantities that you measured in the lab. You have x and y. X has its own uncertainty and y has its own uncertainty, because these are measured quantities. Always measured quantities, they have uncertainty with them. Now, nothing wrong with this. We just learned how to do this, how to find the average and uncertainty and so on. Now, let me ask you this. What if there is another quantity, which is a, for example, that is equal to x times y plus x squared, for example? Now, a is a calculated quantity, but you are going to calculate it by using these measured quantities. So, to calculate a, it's very simple. It's simply x times y plus x squared. Very easy. However, how would I find the uncertainty in A? Now, the propagation of errors answers this question for you. So there are a couple of rules that are easy to grasp here. If the calculated quantity is equal to x plus y or x minus y, so in other words, for the case of addition or subtraction, then the uncertainty in this calculated quantity, which is A, is equal to delta x plus delta y. If A is equal to x times y or x divided by y, so in other words, multiplication and division, delta A over A is equal to delta x over x plus delta y over y, and then you can solve for delta A, because normally you have all other quantities. Let's take an example. Let's say that we want to measure his and his car masses, and we're interested in the total mass. If M1 is the mass of the car, which is given as 1500 plus or minus 10 kilogram, M2 is the mass of this man, and it is 95 plus or minus 1 kilogram. And let's say that somebody like maybe this guy is interested in the total mass for some reason, and he is also interested about the uncertainty, like he's scientist or something, or science-oriented person. Then let's help him out. First of all, the total mass is very simple to calculate because it's the sum of the two masses. So it's 1500 plus 95, and this is 1595 kilograms. Very simple. Now, to calculate the uncertainty in the total mass, notice that this is an addition. And in case of addition, we have to use the first one, right? So the uncertainty in the total mass is equal to the uncertainty in the first mass plus the uncertainty in the second mass. So this is how you should write your equation. And then simply plug the numbers. The uncertainty in the first mass is 10 kilogram, and in the second mass it's 1 kilogram. So you have a total of 11 kilogram. Now, once you have this information, now we have the total mass and we have the uncertainty in the total mass, then we can write our full answer as M total is equal to 1595 plus or minus 11 kilograms. Now let's take another example, and let's say that you want to measure the density of a sphere or something spherical like this cat, maybe. And let's say that you are given its radius and its mass. Okay, so both of these are measured quantities, and apparently they have their uncertainties. Why would we measure the density of such a thing, you may ask? Maybe somebody like this guy is interested in it. We don't know. But let's calculate it. So we know that the density is equal to the mass over the volume, which is equal to the mass divided by 4/3 pi r cubed, assuming that this cat is a perfect sphere. Now, this is very simple to calculate. Just grab your calculator and you can prove that the total mass is like this. If you do the calculation and you found that I am wrong, that will be unfortunate because I would ask you to send me a feedback, and I will have to review this video, and then I have to change my video or edit it, which will be unfortunate. So now let's talk about the uncertainty, which is where the nice things happen. Let's rewrite the density so that instead of the cube we have m over 4/3 pi times r times r times r. Okay, because we gave you only two relations, one for addition and subtraction, and the other one is for multiplication. So now our relation is simple. It's very clear that this is multiplication and division. So this means that we have to use the second equation. So you can see that we have four quantities. We have the mass, we have the radius 3 times. So delta rho over rho is equal to delta m over m plus delta r over r 3 times, right? And then you have all of these quantities except for delta rho. Rho, we just calculated it. It's 334 kilograms per meter cubed. So just plug the numbers from above and you'll find that delta rho is equal to 15.6. Don't stop here because we have to write the unit as well. Very important. Because we like to take off points for not writing the units. So once you have the density and its uncertainty, once again we can report our answer as rho equals 334 plus or minus 15.6 kilogram per meter cube. Now let's take a look at something called percent error and percent difference. Now let's say that you measured the radius or the diameter, sorry. Let's say that you measured the diameter of this bearing using the vernier caliper as shown here. And you've got the answer. It's the experimental equals 4.62 centimeters. And let's say that somebody like so this value is called the experimental value of D. Okay, the experimental value of the diameter. Now let's say that somebody like this engineer or this CEO of that company told you that they are confident that their bearings have a diameter of exactly 4.5 centimeters and that they used sophisticated equipment to measure them and they use very sophisticated equipment in the quality control, so their bearings have a 4.50 centimeter diameter. So we call this, in that case, the theoretical value of D. Some textbooks or some people like to call it accepted value or known value. All of these are the same, so don't panic if you hear other expressions for this value. Now, since you know the theoretical value of your measurement, then you can calculate something called the percent error, which is given by the difference between these two values divided by the theoretical value. And of course, you take the absolute value, so it's always a positive number. So in our case, it's 4.62 minus 4.5 divided by 4.5 times 100%. And if you use your calculator, you'll find that it is 2.4%. Now the percent error is a measure of something called the accuracy. Now the accuracy is how close you are from the theoretical value or from the actual value. Now let's use the same measurement from our previous example. And let's say that another student, for example, did the same measurement or repeated the measurement of the same bearing and the same diameter, and he obtained another experimental value. Now we have these two experimental values. Let's call them D1 and D2. Now, when you have two experimental values, then you can calculate something called the percent difference, which is given by the difference between these two values divided by their average times 100%. And notice that we have the absolute value, so it's always a positive number. Now, in this example, if you use your calculator, you'll find that the percent difference between these two readings is 4.65%. Now, if you are the one that did the two measurements, then you can use this to show how precise your data is. So this can be used as a measurement of the precision of your experimental data. Now, the precision is how much your data are close to each other, or how reproducible your data is or your result is. Notice that this guy has a very good precision and accuracy at the same time. And the reason is that his values are close to the actual value, and also they are reproducible, so every time he hits the same target. So this is a good example on accuracy and precision at the same time. I'm not sure if he cheated or not though.